my share to ground. Now, find out what it is now. Little down, little up. Whoa. And it's not far from 9. It's between 8 and 9. Half 18 would be just 9. And it's a little less than half. But it's not far from it. Swing out the other ball, please. And share 50-50. Bring it in. One span, please. Actually, I don't need to do this second test. I appeal to symmetry. We already know the force is proportional to one charge, so it must be proportional to the other charge. After all, how do the balls know which is which is agent and which is victim? But in fact, I see the force is just about 4, just about halved. So we can say that the force is proportional to each of the charges. So now we can return to our original statement. Force is proportional to number of elementary electric charges in excess times number of elementary electric charges in excess over distance squared. Some of you may think that we have proved Coulomb's law, and others may say this is just a poor, rough test. But the wise scientist develops a taste for good form in laws, and can often jump to the right law on poor evidence. Such rash, clear-sighted guessing is good science, if the result is then tested. So I ask you to accept the inverse square law for the moment, and watch while we make a magnificent sensitive test based on good theory. Good theory is not just wild imagining, but argues with sober, hard-headed reasoning, like this. If, then. If, thus, then. I shall argue, if Coulomb's law holds, then, if we have a large hollow metal ball with an electric charge, we find no electric effect inside. And the converse holds. If there is no electric effect inside a hollow charged ball, there must be an inverse square law of force between charges. Here's the argument. We have a large, round, conducting ball. Give it charges, say plus all over like this. And then look for electric effects. Outside, we shall certainly find some effects. Would you like to see the ball? A large copper ball, hollow, so that we can investigate inside. Charge it up, please. Take a sample from outside on a metal ball on an insulating rod. Bring it across to my electroscope. There's plenty there. Now let's get back to the argument. Suppose we put two small metal balls touching each other very close to the big ball. Then these make all one conductor, and this big positive charge pulls negative electrons this way, so that we shall get negative charges all over there and positives left here. Then if we separate these two and carry each in turn over to an electroscope, we shall find charge and charge. So much for outside. Now let's look inside. Suppose we put just here a demon observer carrying a test positive charge there. He looks up here at a patch of the copper ball, like that, carrying positive charge all over it. Then this charge will repel his test charge like that. Let's draw a cone of lines down through the edges of the patch. There, like that. There. Then, as well as looking up to a repulsive patch there, he looks down to a counter cone here, to a counter cone, to a counter patch down there. And that patch of positive charge will push up this way. How will those two pushes compare on his specimen plus charge there? Look at the distances. So much, and so much again. this patch is twice as far away from him as that patch. So this cone has spread out to twice as wide and twice as broad there, 4 times the area of that patch. We shall assume that charge spreads uniformly all over the sphere. So there's 4 times the charge there that we have down there. On that score, the repulsion is 4 times as great due to this as due to that. Now remember the inverse square law. If that holds, this is at double the distance of that, and so we shall have 1/4 of the effect at double distance. 4 times 1/4 is 1, so that this repulsion will be exactly the same as that repulsion. And the 2 of them will exactly cancel out like that. You see, on the score of area and charge, we've got 4 times as much there. On the score of distance, the effect is only 1/4. Now we can install another patch next door and put another cone here, and another patch, and cone, and counter cone, patch, and counter patch. Oh, I know these are getting oblique, but the tangents at the end of a chord make the same angle at both ends with a sphere, and so the obliquity factor is the same at both ends. And so we can put patch and patch and patch and patch and fill the whole sphere with cones, each of them making a pair of forces that cancel out. In that way, we shall get inside 0 total force on a test charge, 0 effect if we put 2 little balls together and then separate them and take them out to our electroscope. So if the inverse square law holds, we expect no effect inside a sphere. The converse is true. If there's no effect inside a sphere, then the geometry of the areas and charges still holds, but if there isn't an inverse square law, just to undo the area factor, we shan't get 0 inside. So this gives us a very critical test. Now let's try it. First, we'll try it outside. 2 balls touch together near the sphere, separate, and take first one, the electroscope, and then the other. Notice the other brings the opposite charge, drives the electroscope lead down. We should expect very little left. Discharge both those. Just make sure the electroscope starts at 0. Now we'll investigate inside. We go carefully into the sphere, and inside, touch the 2 balls together, bring them out, separated. Try this one. Nothing. Nothing. That's our test of the inverse square law. If you want to see a more gross test, let's just take a big charge from outside, plenty, as before, and then go fishing for a charge from the inside. Listen. That assures us of an inverse square law. It's a very good test because it asks for an answer 0, what we call a null result, and it only needs very sensitive apparatus. It has been tried to an accuracy of 1 in a billion. No electric force inside a hollow charged sphere. Complete shielding. And now let us test our test by taking away half the geometry. We can do that by taking away half the ball. Then we shall only have half of each pair of cones, and we shall expect something inside. Now charge it up again, please. Take a sample from outside to the electroscope. There's plenty there. Discharge the electroscope. Necessary, discharge the ball. Take a sample from just inside. You won't go too far down, but we should expect less further down. And we do get something. Take another trip, just inside. We get some more. So you see, this test of the inverse square law does need a completely closed sphere, or at least one with only a small hole. The argument extends further. The result we got for a hollow sphere applies to any closed metal box. It must be closed, and it must be a conductor. The geometry for other shapes goes beyond this course. The charges do not spread evenly all over the surface, but concentrate along edges and corners in such a way that they produce exactly zero force everywhere inside. The small hole doesn't matter. Our sphere had an open mouth, and we can even use chicken netting. Remember, this only applies if the inverse square law holds. But the inverse square law is true, so any metal box and even a wire cage will give complete shielding. Come and see that tried. I have here a large metal table on insulating feet, and I'm going to ask my junior assistant to stand on the table. Comb your hair, please. And then we're going to charge up table and assistant and cage and everything. This wooden rod is a poor conductor. Start up my charging machine. When I connect to ground, all the charges run away through the spark. The leaves fall, the hair falls. This time, nothing happens in the cage, whether I connect to ground or not. Hold the rod to me. Take away the charge slowly. Now step off. Thank you very much. A good scientist likes to keep a flexible mind and turn his knowledge to different uses. With your present knowledge, try to answer this problem. What would gravity be like inside a hollow earth? You may imagine it to be made of thin shells like the layers of an onion with a hollow inside. What would you find inside? I'm not going to answer that, but you can with the same argument. Look back on the way we developed this knowledge of law. We started with rough experiments and made a guess with the gravity law as a model. And then we tested our guess and found it probably true in one example. So we stated it as a rule for distances and for the sizes of charge. Already you can use the rule to compare the sizes of charge. Put each charge in turn at the same distance from some standard charge and compare the forces they exert. Then we assumed our rule is true and devised a sensitive overall test. No force, no effect inside a hollow charged metal ball. That gave us such assurance that we call our rule a law, and we trust it far and wide, from thunderclouds to atomic nuclei, and we shall continue to trust it until we find an exception that makes us modify it. Here, in Coulomb's law, we have a summary of nature's behavior. It is part of our scheme for understanding electricity, not by knowing what it is, but by codifying what it does.